Logarithmic functions are the inverses of exponential functions. So what I have, y is equal to a to the x. A logarithmic function is the inverse. In order to find the inverse, I need to switch the x and the y. We figure out what that is, and then we came up with this new notation to describe that, similar to the way where this hat was invented to denote the inverse of a square function, the square root. The logarithmic notation was invented to indicate the inverse of an exponential function. And in an inverse function, the y's and the x's are switched. So this y is essentially this x, and this x is this y. And the reason I bring this up and explain this over again is because that means our graph is going to be an exponential function, but with the x's and the y's switched. And I do this because logarithms at this point are not necessarily intuitive, very intuitive at this point. So sometimes it's difficult to think in terms of logarithms at this point, and it's easier to think in terms of exponential functions because people have been dealing with them for longer. So in order to make this graph of a logarithmic function, I'm going to begin with the graph of an exponential function. It's really crooked. Should be good enough. And I'll just take some basic points. -3, -2, -1, 0, 1, 2, and 3. And I'll pick a base of 2. Y is equal to 2 to the x. Now let me get some points. I'll start with 0 because it's an easy one. 2 to the 0 is equal to 1. 2 to the first is equal to 2. 2 to the second is equal to 4. 2 to the third is equal to 8. And the negatives of an exponential function give essentially the same numerical value as the positive one, except it's the inverse. So -1 is the reciprocal of 2. That's 1/2. And -2 is the reciprocal of whatever 2 would be. So this is 1/4. And then -3 is the same thing, so it's going to be 1/8. So now that I have my points, I'm going to make a quick graph of this, and then it will be much easier to compare it. So for -3 I had 1/8. For -2 I had 1/4. For -1 I had 1/2. Oh, these are shifted over by 1. Oops. That was -4. This is -3. That's 1/8. This is 1/4. And this is 1/2. It was 0. It was 1. For 2, or for 1, it was 2. For 2, 4. And then for 3, it was 8. And that's off the graph. The graph looks like this. And this is y is equal to 2 to the x. Now I started this off by talking about that logarithms were the inverses of exponential functions, which means that the y's and the x's are switched. So the graph of a logarithmic function is going to look like this graph, except the x's and the y's switched. So what I can do for coming up with a table of values is I can use the same table of values I have, except switch the x's and y's. Now assuming this is a base 2 logarithm, it wouldn't work for a base 3, it has to be the same base. We'll do this in a different color. We'll say that y is equal to log base 2 of x. So here, the x's and y's are going to switch for this one. So I'm going to use the x's of 1/8, 1/4, 1/2, 1, 2, 4, and 8. And remember, a logarithm is basically asking what exponent of 2 gives x. So what exponent of 2 gives 1/8? That's minus 3. What exponent of 2 gives 1/4? Minus 2. What exponent of 2 gives 1/2? Minus 1. What exponent of 2 gives 1? 0. What exponent of 2 gives 2? 1. What exponent of 2 gives 4? 2. What exponent of 2 gives 8? And that's 3. So now it's easier to understand just how logarithms work in general, but just to see what is happening graphically. Now if I put all of these points on a graph, I'm going to start with 1/8. X is equal to 1/8. That's somewhere right here. It's very close. Next I have 1/4, and that's minus 2. Then I have 1/2. X is equal to 1/2, and that is minus 1. X is equal to 1. That is 0. X is equal to 2. That is 1. X is equal to 3. Or x is equal to 4. I'm sorry. X is equal to 4. And that is equal to 2. And then the last point won't fit. Looks like this. So you can see the similarities between these two graphs. This is y is equal to log base 2 of x. They're the same thing, except the y's and the x's are backwards. There really isn't much else to graphing logarithms. And now I'll talk a little bit about the transformations, and there really isn't much to talk about transformations either. Transformations work exactly the same as it would for any other function. If there's a constant being added to it, that means there's a vertical transformation. If there's a minus sign out in front of the log, that means there's a reflection. If there is something being added or subtracted to the x here, then that means there's going to be a horizontal shift, and then a multiplication is going to be a stretching, a compression of some kind. But I'll do a few simple examples just to help refresh. Suppose I have, let's see, we'll just use the same base. Y is equal to log base 2 of x plus 2. So the first thing I want to do is identify the base function. And in this case, it is log base 2 of x. So now that I've identified the base function, I need to see what types of transformations are taking place. And in this case, there's only one transformation taking place. And that is a constant being added to the base function, which means that is a vertical shift. And since it's a positive 2, that means it's an upward shift by 2. And I'll put the base function on here just to have a helpful point of reference. So this is y is equal to log base 2 of x with no transformations of any kind. Now for this one, it's the same as the base function, but just plus 2. That's going to be a vertical shift of 2. So I essentially take my 2 points that I decided to graph and shift them up by 2. So this will look like this. And this is log base 2 of x plus 2. And that's all there is to that. It's very, very simple. But let me do a couple more types of transformations, I guess. Just in case anyone hasn't done any for a while, we'll do a reflection. Y is equal to minus log base 2 of x. Now again, my base function, always start with the base function. The base function is log base 2 of x. Now I look to see what else is happening to it, and I can see that there is a minus sign out front. So essentially I'm going to be getting the exact same values as I would for my regular base function, log base 2 of x, except that they're going to be negative. So it's going to be flipped across the x-axis. So I'll put the base function on. Oh, it doesn't bend downward like that. I'm just bad at drawing. So this is log base 2 of x. Now here I found that there's a minus sign, so this is a reflection on the x-axis. So that means it's going to be pointing upwards this way. So I'm going to take this point that was down here and it's going to be here instead. It's going to be reflected across the x-axis. So instead of having 2, 1, I'm going to have 2 minus 1. And then it's going to come here through the 0. And then it's going to go to positive infinity. That's really bad. It's going to go to positive infinity instead of negative infinity. This is minus log base 2 of x. So real simple stuff. I guess I'll do one more. We'll do a horizontal transformation. We'll do y is equal to log base 2 of x. Let me put these parentheses in here. usually if something's happening to the x in a logarithm, they'll always have parentheses around it, so people don't get confused. And you might want to start practicing that as well so you don't confuse yourself. We'll do minus 2. So here, I identify my base function. I see that is log base 2 of x, and then I look for the transformations. And here I can see that there is a subtraction of 2. Now the important thing to remember, when there is a horizontal shift, that it is the opposite taking place when there is a subtraction or addition to an x. That means instead of when there's a vertical shift, let's say this is a vertical, if it's a +1, then that means it goes up 1. If there's a -2, it means it goes down 2. But here the opposite is taking place. This is not going to the left, it is going to the right. So this is going to the right 2 units. So let me make a very fast graph and we'll be done. So that's the base, and this is shifted over to the right by 2. So I take this point and move it over by 2, and I take this point over here and I move it over by 2. This is log base 2 of x minus 2. This one was log base 2 of x. All the transformations are exactly the same. If you have trouble with them, just go back over the basic transformations and review them.